hope for good. Hopefully it will work. So I shoot a ray out toward the sun, and I get from the recursive ray tracing for this ray R prime, starting at emerging from the point Q, and I'm asking what is the first time that this ray hits any obstacle. Here are a few obstacles, a sphere, a few billboards, and what should I ask? At some point at t equals 20, say, this ray hits the sun. How do I know if Q is in the shadow or not? It looks very trivial, but I'm trying to warn you of a very easily made bug. For each one of the objects, you're getting intersection point. Well, the ray reports, recursive ray tracing for this. You already know, as we said, that from the eye through the pixel, it hits the point Q. Now you want to see if Q is in the shadow or not. So you are shooting away from Q toward the sun, the same recursive ray tracing. And you're getting the question of the minimum T. And based on the minimum T that you hit an object, if T is larger than 20, like if the ray hits the sun at T equals 30, way after that it hits the sun, then Q is fully illuminated. But what are you doing? For each and every object, you're getting some value T1, T2, T3, the time at which the ray hits each one of the objects. And you're asking, is the minimum out of all these objects, is a minimum T is smaller or equal than 30? And if it's smaller than 20, we said 20 we hit the sun. And if the answer is that the minimum is smaller than 20, then Q is in the shadow, something occludes the sun. If T is larger than 20, then it should see the sun. And somebody that already experienced it can tell us what's the obvious bug. Think about it while I'm bringing back eraser. I'll just remind you that the way that the recursive ray tracing, you're hopefully writing it these days, are working is that for each one of your objects, that is either billboard or a sphere, it asks at which time the ray emerging from Q in the direction R, at which time does this ray hit this object. And as we said, if it's a sphere and you completely miss this object, then T is a complex number. If it's a billboard, then in most cases you'll find that you at least hit the plane that hits a billboard, but it doesn't mean that you're actually hitting the billboard, and so on. Okay, anybody figure out? Yeah.
My guess is opacity of each of those objects. If they're all clear.
Even if they are all opaque. I mean, it could be that my description was too vague. That's why you don't see the issue. Other guesses? Even if they are all opaque. The bug will be that you are very likely to decide that Q is in the shadow. Even in this case, that it has very straight line. There is no object that hits the sun, but that is the only object happens at t equals 30. But what is the minimum t at which the ray hits any one of the objects? Again, the bug will be that you're almost surely reporting that Q is in the shadow. Because does Q intersect any object?
Is it intersecting the light source?
It will intersect the light source, but it asks for the minimum t. It goes in this way, and at t equals 0, it intersects where the ray was emerging. At t, you're checking intersection with all the objects, including this sphere that I started with, that where the sphere has a point that I'm asking, this point is in the sphere, is in the shadow or not. But the recursive ray tracing doesn't know that the ray emerges from this particular sphere. It reports, yes, the ray intersects the sphere exactly at t equals 0. And unless you're excluding this t, then the minimum time is t equals 0. It does intersect a sphere, even though it doesn't really block the light. So it means that it needs some attention and some hacking. So you will decide that the time happens only if there is some small epsilon. Except that finding the right epsilon is not trivial. Maybe it's a small, very small, maybe it's a very small sin. Or let's move the starting point by a bit. So you need to hack it somehow. There is no one solution that solves it all. You need to somehow hack it, and especially when we are using the depth buffer for the shadow map, it will be even more annoying to start it, because then the number of digits that we have for the depth is quite limited. And to decide if the sun sees an object or not will be more of an issue. Here it's just a good source of bugs, but once you're aware that it could happen, and it's not 3 a.m., and you're probably okay with the shadow, generating the shadow. Okay, and as we said, be careful not to intersect with the object itself. For example, all the points on the carpet reported that they don't see the sun because they intersect with the carpet itself. Wrongly, the same goes for all the points on the sphere themselves. So two solutions is check for hits against all other surfaces and be sure to identify that you are not your own surface, or start the shadow ray tiny distance away from the hit point. So Q, where I start to go the way, is not on the sphere itself, is slightly away from the sphere. Remember, because you are building the ray tracing in a recursive way, do not build it in any other way because you will need it for actually sometimes. Recursive with more level of the recursions, definitely in the future homeworks, but even in this homework you are using it in the same twice to shoot rays from the eye to the surface and then from the surface to see if it's in the shadow or not. You need to use it twice or use it recursively, so it doesn't know that it's from which object it emerges. Okay, recursive ray tracing, what you're doing, you have the two spheres, you start with their initial color just based on ambient, and now you're trying to ask, do you see the light? If yes, and in which angle am I to the light? Creating the diffuse effect, creating possibly the specular effect. Each time for each pixel, just add one more level of the colors. And if you want to go with more depth of the recursion, then look at the rays that just hit this spot where my finger is. You're asking what is the color of this point of this in the original image. And the answer is depending on the depth of the recursion. If my depth of the recursion is only 2, hit the object and emerge from the object, then this point is just any other point on the carpet, gray. If I'll allow another level of the recursion from this point, do I hit any of the other objects like the blue ball, then now I have the blue ball, the blue sphere. Reflection on the table itself, so these pixels becoming blue, these pixels becoming green. So more and more levels of the recursion, if you want. Okay, shadows. So surface shadows only illuminate if nothing blocks the lights, assuming that the light is the source of light. Okay, object here blocks, then it's in the shadow. And this is easily checked by intersection new ray with the scene and a ray from the hit point towards the light here are blocked by some other surfaces. Of course, that's assuming that it's point source of light. These lights will have different discussion because it's not surface points of light, and we'll get today to how do I handle such surfaces or non-point source of light. Just ray terminology, ray casting versus ray tracing. Ray casting, trace a ray from the eye until it hits something, and then you're done, one level of the recursion. Ray tracing, once the ray hits an object, what happened to rays emerging from this object? Okay, or do ray tracing now from the sun towards the object? Both are legit. That is, it's fine to ask from the sun what does the sun illuminate, and then do only one level of the recursion from the camera, or to first do one level from the camera and ask where does it hit. But if you're doing 2 levels of tracing, then it's not clear that I just need to shoot a ray to the single point source of light. As we discussed many times, there is reflection from the walls as well, reflection from the objects as well. Let's do more reflections. And let's talk about a problem that looks a bit minor and maybe application limited, but the tools that I'm going to describe will have many other applications. So I'm going to describe a distributed and stochastic ray tracing. But the motivation for why distributed ray tracing, let's just talk about hard shadows. Hard shadows, very easy. This point of the carpet, don't see the sun. The ray from this to the sun hits the ball, so this point is completely dark, no ambient light. This point is completely in the light, completely illuminated. So, and between the shadow, the shaded area versus the non-shaded, very clear boundary, so we called it hard shadows. And yeah, don't again, oh, sorry, I went backward. So hard shadows, we discuss them. Well, of course, the solutions for the 2 hard shadows, didn't realize this slide twice. Distributed ray tracing. So look at these shadows and at these reflection of the red ball in the mirror ball, or the shadow over here, very, very clear shadow, that you'll say maybe it's acceptable if it's only daylight, but it will never get with multiple lights or non-surface points of light. Or it's very strange that there are such hard shadow, because it means, what do we mean hard shadow? That no other object besides the sun can illuminate this point. No other object reflects light into it, which, unless the scene is completely empty, makes very little sense. So it looks very unreal. Maybe you don't care, but if you want to look at arguably better, maybe more realistic, then you realize that nothing is a perfect mirror. No, and definitely not if it's not even aiming to be a mirror. Just it's reflective, but not exactly a mirror. It's not perfectly smooth. What does it mean? Idle specular in a mirror will means one ray is emerging in this direction. One ray is going into the object if it's glass-wise or water-wise, but it's only one way and one way, single and single. What happened in glossy but specular reflections? That we discussed. We have one ray that is reflected in the direction of the perfect reflections, but you also get rays that are emerging in directions that are very close but not exactly perfect reflection. Lamberian just says that the ambient light doesn't care which direction, goes same amount of light reflected everywhere. Glossy is where we are more relevant right now. It will be not a single ray, but also not a lot of rays. We want to meet a sweet point between the single ray versus multiple rays. So most surface had this microgeometry, has little texture in 3D that implies that I have reflection in many directions. That's why all these surfaces have this smooth look around them. But so what we discovered as the moon paradox, just in a much, much smaller sense. Remember, moon paradox, why all the direction of the moon were uniformly illuminated, because for every point of the moon I had normals that pointed towards it. Same goes here. What happens if I have this macro surface? But I definitely don't want to model this micro behavior. I don't want to have a geometric description of exactly the surface, but I want it still to look like it's 3D structure. So instead of idle reflection, one way, we will have several ways emerging with different intensities. Okay, but instead of one way, several ways in several directions. Okay? Instead getting a glossy look into it will be, let's shoot a few rays from each point in small distribution. And that's how we collect the light. I want to know how illuminated this point of the wall is. I'll ask for each I'll ask if this point sees each one of the lamps, a few rays toward point source of light, but I'll also shoot a few rays in the walls in random directions, distributed directions, to ask, does it a lot of ray that coming from any particular direction from other walls, not from point source of light. You'll see more coming over this discussion of shooting rays in distributed direction. So distributed glossy reflection by randomly samples. If I want to ask, this point is illuminated because of reflection from other sources of light. Maybe this point is less so. Let's find a good point. you can see what happens underneath the whiteboard, even though this point does not see the light. You see, the reason that you see the reflection out there is because of reflection from other objects, the same reason you see underneath the chairs in this room. Okay, so I don't want to shoot many rays, but I don't necessarily know, for the few rays that I do shoot, I don't necessarily know to which directions. So people that took algorithms with me know my general mantra. If I don't know what to do, pick a random direction. That's essentially what we're going to do. Random doesn't mean uniformly distributed, but it still means I'm going to throw some points. So again, ideal reflection, one ray per bounce. Glossy reflections will mean that I want to know what's the color right here. I'll shoot a few rays, see, do I see the purple ball? Do I see this point? This point over here. Do I see the orange ball? Do I see the cayenne ball? Do I see the purple? And if I shoot 10 rays and 5 of them will say I hit first the orange and one will hit the other ones, then the color that I assign to this point would be some average of many rays hit the orange, so much more weight to the orange and much less weight for the other rays, depending just on how many of them hit each one of the objects. So my color will be the average, the weighted average of, for each ray, what did this ray claims to be the first object that I hit. Make sense? Let's have the 2D analogy. First, Monte Carlo algorithm. You want to know what is the area of the shape A. How many square feet are there in A? I can compute the integral, maybe. Maybe the boundary is not such a nice function, so I cannot compute it directly. I can divide, create a very nice grid, exactly D unit apart. Zoom it out. D units apart exactly between each two grid points. But if D needs to be really, really small to be relevant, and I still might miss it, right? If my shape looks like this and I'm putting a grid, I can be way off. Because this shape can have large area and still meet very few grid points. So what's the answer? Monte Carlo method. It will say, instead of assuming that I can at least easily, for a given point Q, I can ask, is Q inside A or outside A? And I assume that the overall area is 1 to 1 straight. Then let's pick a random sample of points. A law, again, doesn't mean necessarily uniform, but random sample of points. And we'll argue that say that the area of A, if this is 1 by 1, would be K, what? It's the number of sample points that actually fall inside A. That's of course wrong. If that's 1 by 1, then the answer should be, help? Divided by by total number of sample points. And now it's more reliable than a grid. Again, with high probability, you'll get the correct answer, the correct area of A. How many of your points falls inside A if the total area is the portion of A divided by 1 by 1? So that's exactly what we are doing, asking average answer of shoot in some random directions and accumulate how many times did you hit the orange, how many times did you hit the, how many times did you hit, did you hit each color, takes the random average. That's a value that you'll get. And that's how you look, which maybe you like it, maybe not, but it looks at least more realistic, the sphere. It doesn't look like infinitely smooth. And you see the reflections. Let's meditate on it a bit more. And with reasonable computing time, the boundaries between the bricks between the bricks on the floor are very well defined, but look at the reflection of these bricks on the sphere. The sphere is not smooth, meaning that the reflection direction has some distribution on it. So the color right here is some average of colors that I looked from a few areas, but I can still see the reflections of the bricks in the wall, just more realistic. Question?
Yeah, so if we're back propagating the rays from the camera to this sphere, and then we're picking, basically we know the, how do you do this? I guess my question is, how do you do this when you're backwards ray tracing, like from the camera to the sphere? How do you evaluate this polished surface BRDF in reverse? Right? Right, because
so
the ray...
I assume that I know the normal, and the projection from at this point would be as if it's perfectly smooth, plus minus some noise, so I'm still heavily biased towards the normal. Think about it as a perfect mirror, and then add a bit noise to each ray. For each ray that you shoot just in the direction of the perfect normal, add 3 other rays near the normals with small angles at random.
So how do you ensure that those rays eventually reach the light
it's
source?
stochastic. No.
Okay.
It's the color that I assign to this point is in the shadow or in the light. Much easier when it's a point source, light source. So I'm heavy, so I'll definitely check if I'm in the sun or not, if I assume that there is sun involved. There is one image that I'll get to, that I will get to the image. So I'm very biased towards the illuminated area. But if on top of it, so from each point I ask, is this in the dark or in the light? But if I want to assume that there is also higher order of the recursion, the reflection of the surface in the surface, I need to shoot a ray from this sphere that hits this brick and ask, is this brick illuminated or not? So now a ray to the light from the brick again. So that if I only have 3 directions, they hit each point, and now from each point I see, is this point see the light?
So once you figure out where the secondary ray hits, you then ray trace back from the point source to figure out the illumination of the secondary?
Yes, unless I think that there is some reason that this is so shiny, or that reason that I need to now head at another level. It doesn't need to be uniformly the same level to each depth of the recursion. If it's highly illuminated, or I think that it's highly shiny, then I'll sample it in a better way. I'll assume that it's only other or matte object. What you'll do in maybe homework 3, definitely later homeworks, is the first hitting point you will not do via ray tracing. You'll use the depth buffer that will approximate for you where each ray hits. So that will be done in hardware. And then you use some other tricks that will tell you what is the color at this point using texture. And if maybe that would be enough if you're good with flat parts, but it doesn't introduce any specular and diffuse reflection. If you want to add specular and diffuse, then now from this point, still in parallel, from the first hitting point, I'll see what the light contribution, but that I'll have to implement myself. That's not what the Z-buffer gives me. Okay, so other applications, let's go really quickly. Other application of ray tracing would be like the fuzzy direction over here, because from this point I did shoot a few rays to see where do I hit the spheres. Right. Again, it's random direction. Definitely, I can miss the correct answer. It's randomized. Right. There is a technique called global illumination that try to solve everything as a huge system of linear equations, and it's very clever. Maybe we'll talk about it, but it's very, very slow as well. So, in one way, we said it multiple ways. Another example, distributed ray tracing. Once again, from point source of light instead of one source. Multiple sources, more examples, instead of the hard shadows, soft shadows. Why do you see these soft boundaries? Because it's not point source of light. It's like these lamps. It's a surface. So I need to shoot several rays and ask what is the contribution. At this point, all the rays toward the surface of the lamp, all hit the surface of the lamp. This point, none of these rays toward the lamp hit it. And here on the boundary, some rays do, some don't. And that's why you are getting the soft boundaries instead of the hard boundaries. Okay, cool example. Once again, is this a point source of light or a surface source of light? It's surface. It's definitely not a single source of light. Otherwise, the boundaries of the shadow, you see gradual distribution. But let's see more applications toward it. Yeah. That's for the sun. If you want to think about the sun as head size in it, I really love this picture. I think that's a great application of distributed ray tracing. So the basic scene, you've seen the PDF with all details. There is a room that you can see some details of the room out here. The projector washed them completely. So there is some details over here. Obviously, window highly illuminated, but see the gradual changes of the illumination for points on the wall. What do I do for each point over here to get this realistic effect? I shoot several rays to the direction on each one of the surfaces. Some of the points stays within the room, meaning that they report very little light coming from within the room because it's dark. Some of the rays hit the window, which is very highly illuminated, so this point is bright, nicely illuminated, and more of these rays hit the window, the closer that I'm getting to the edge of the window. Right? See the gradual effect of moving from this side all the way to this side. Because more area of your surrounding is exposed to the window. Okay, more about computing ray tracing. Hey, I mentioned aliasing. Yeah, we will not summarize it today, but here is my shape. The shape itself is black on a white background. I can render it in this way, so every pixel is either inside or outside, and this gives me the staircase, or I can assign average value, average level of gray, or average value RGB for each one of them, based on how much area is inside the shape, how much area is outside the shape. Except that you really want to stay away from computing the exact area of the shape. Unless it's a rectangle or something really simple, computing intersection of areas is ugly computation. Instead, sampled within a pixel, sample a few points, and the average and the gray level that you assign to the pixel is the average of how many points hits the black, how many points hits the white. The average of the two values, but average depending on weighted average. Right? If 90% of the points hits the black, then you're 90% are there to the black. And that's how you're creating the anti-aliasing effect, basic idea of anti-aliasing. What about the Moore pattern? So this is a picture of the brick wall, classical example. That's just the image without any processing of a brick wall. And notice this is some dark area, dark strips alternating with white strips. Even though each brick has the same area of black and white. But all see it, there is these curves over here called Moore pattern. Why does it happen? Because I sampled in not enough frequencies, but in a uniform grid. I could have avoided this strange pattern and it would look normally as it, if I would increase by much the sampling rate. But let's try to understand why does it happen? Why all this shape happens? I think that I have another slide on it to add the Moore pattern. Again, anti-aliasing to avoid these ugly staircases, and Moore patterns jiggies versus with anti-aliasing of the sphere. The Moore pattern, because at each pixel I sampled only once, and what happened, that's how the wall should have looked like. And that's what the wall looks like when I'm using uniform grid. I don't like, if I don't like randomized algorithm, I will sample always, even sub-sample within a pixel, but always within the same distance, uniform grid. Quite likely that's what will happen. Why is this? Because the frequencies of changing from white to orange in the wall that you see over here, sometimes I'm sampling just exactly at the white gaps between the bricks, and sometimes I'm avoiding the white samples all, depending on where did I sample the white bricks. Again, if I'm sampling, if every center of a pixel happens to be on a gap between two bricks on the white area, then the pixel will be fully white. If my sampling are only on the center of the bricks, then I'll get something that is much towards the gray. And as I'm playing with both patterns, they can definitely create these more shapes out of solutions. Use inside pixel, use a random sample. That's to start with, it's a good strategy. Inside a pixel, you think what is the color that is reported, the rays that you hit, but do it for a few points, picked at random. Or even better, and that's like the textbook solution, is if I sampled small number of points at random, there will be too many areas that I'll miss. If I'll always sample in the center of every subpixels, then I'm running into aliasing issues, sampling that I'm just hitting much bias towards the red or much towards the green. What would I do? Subdivide into subpixels, and inside every subpixel, making sure that every subpixel I will sample, but it could be 1 point, maybe 3 points, will be not be necessarily at the center of the pixel. So I'm balancing both structure of one pixel into subpixels, sampled from all of them, but where do you sample inside the subpixel? That's where you are using the randomness. Make sense? And we'll see plenty of other applications of this subsampling, as well as understanding what this aliasing and the Moore patterns and why did they come up and how to avoid them. Cool. You're very quiet today, I must say. Okay, look. So, thanks. Yeah, time to go. Thanks. Yes. Questions?
Hi.
You want to go skating with Thursday? Thursday night?
Maybe.
For homework too, I think I'm confused on how to do the rate. Like I know, like I can read in the JSON file and compute the normal everything fine, but then when it comes to actually, I think when shooting like ray tracing, shooting the rays, that's where I'm like lost. I'm not sure.
Okay, let's talk about it.
Well, there's two
Do you get anything? I suggested to start with a much smaller resolution. Yes, so
yeah, I tried just because I think it says if you don't hit anything, then you just display blue. So then I think I initialize all pixels to blue, and then I tried doing the ray tracing, and then when I like save the GIF, the whole picture is just blue. So I don't think any of my like ray tracing is
But
working.
do you display it to you? Do you have any idea what's happening? I
don't
suggested to start with reduce the image and to much smaller 5 by 5. So you got, so it will not run forever. And then I can create for you JSON that will be, say, just check JSON. That would be one billboard, that would be black, that's the west, that would be white, and the image plane would be somewhere here. So you know that the image that you are expecting is half black, half white. But I can definitely create a JSON file of this example and use this to debug to see if you identify that you at all hit the billboard.
But not yet.
I think when I calculate the intersection of a ray and a billboard, I think that's also wrong. I think maybe I'm not doing it correctly.
Let's see.
Yeah.
No, because I don't need parents.
I know, but like if you, because this is technically through Raytheon, right?
No.
Or a subsidiary?
It's a company that contracts with Raytheon.
Oh, I see.
It used to be part of Raytheon, but they kicked us out 5 years ago.
That's crazy.
So I think,
You want to?
Because I know,
oh,
like,
it's okay.
companies like that, where if you ever get like promoted to a more important position, you know,
I think it was this slide,
you know,
maybe.
vouch for security clearance.
There's not much lateral movement in this company.
Yeah, I think,
but it does give me like.
so the equation of the plane is h, where it's the normal times the upper right? I think I have that.
She's like a few people up, but she's in the office. She's in the office.
Yeah, so I have,
She
and
works for Raytheon.
because inside the billboard, I save the U and the V, which is just
Okay, and you normalize them?
yeah, or no,
Like last year I didn't suggest to normalize. This year I did suggest to normalize.
I think
you can solve either way. You just need to be aware. Which one.
I don't
but first-
normalize them. But then when I calculate the normal, I normalize the normal to the plane.
That's good, but if if you're using this year's slide, then I normalize also UNV.
Okay.
You can go in either way, but let's ask: do you hit the plane that contains the billboard?
I think maybe I'm calculating it wrong. I'm not sure. Whatever. So then, like, say you have the billboard. This is U. This is V.
Mhm.
Then U cross V gives you N, which is this way, the normal.
Correct.
Yeah. Then the equation of the plane, so like, I think just this entire thing or whatever would be N times, or N dot upper right. So this upper right, N dot upper right is the equation of the plane.
And well, you can represent the plane in many ways.
I think what you have in your slide is
Yeah. N times. N times x, y, z equals n times pick any point, say lower or left, or doesn't matter. And that's dot product. And
I think.
and there's many things that can go wrong, so I would either print every step or use GeoGebra to check it for one billboard or take one example, but just to not get stuck. So go over it. Now I have the I plus O times R, where R is normal.
O is
times
the
T R. I shoot one way from the eye to one of the pixels. That's already one pixel. So you assume that you have the recursive procedure that takes into account, that takes the O and R, where it emerges from R, and inside it, it goes through all the objects, O1, O, and this recursive call will give you the minimum time when it hits. So let's concentrate on one of the objects, the billboard. Again, other debugging is just create a scene with sphere and see if you're good with spheres only.
I think I have the sphere equation correct as well.
Sure, but it sounds very scary way, for me it sounds scary, to wait until everything is in the GIF and then look if the GIF makes sense. Like, if you're a very good programmer, great. For me, I would never hit it right. So I would ask for at least a control image after each time, and I would. So the first check is, do I hit T? When I hit the billboard, do I hit the billboard in the right point?
This I plus TR is
Times N equals N times point on the billboard. From this you are getting T, I get the formula.
Okay. Oh, yeah. Wait, R is look at, like the look at, right?
No. Okay, let's go over it from the beginning. And there is multiple UVW, so let's stop. I compute I and look at.
Yeah.
This is a vector that gives you W.
Yeah. W is equal to, well, this way would be that. So I minus look at, and then you normalize. Yeah. and then U is
Now we are using the up vector in
up
W.
cross W, and V is W cross U.
Yes, I cannot tell you that quick if it's this or the other way around,
I
but
think
it's in the slide.
That's what I have, yeah.
Let's see that it makes sense.
Up times W, yeah, would be right. Like up cross W
Yeah.
would be that. Then
Mhm.
W cross that would go up, yeah.
So you said up times up times
So
W.
W is this way and
Yes.
U is this
Yes.
way.
Yeah.
So when you cross
I
that,
agree.
yeah. And that's
Now I have
and
the camera coordinate system.
yeah.
Next step, compute D, the distance.
Oh, that is
Distance to
one-
the image plane.
1 over, I think,
Tan.
tan alpha over 2.
Yeah.
Yeah, I have that as well.
Next, the image plane would be, the corner of the image plane would be I plus D minus
Minus
W.
DW, yeah.
Plus minus U plus minus V.
V, yeah.
That's the corner of the image plane. From
But
which now
U-
I
U
spring.
and- This U and V is for the image, right?
Correct.
So like, you have the image, you have lower left, upper right, lower right, and then this is U, and those are the U and V.
Yeah, for the image plane I didn't use these letters, but it's fine.
Yeah.
Just remember that the image plane is from -1 to 1. When
Yeah.
the formula that I used for the billboards, it was from 0 to 1.
Oh.
Image plane is -1 to 1. That's why it's plus minus U.
Yeah. Oh, wait. Okay.
We'll get in a moment to alpha and beta,
Mhm.
but wait with this. So now I generate pixels. How do I generate pixels? I say the image is 10 by 10, so the image plane will be from -1 to 1 would be 5 until the 0, 0, and 5 after the 0, 0, and similarly here. So D. So I minus D plus minus W, etc., gives you each one of these
Each
points.
pixel, yeah.
And this part, by the way, every textbook will give you more or less the same thing, except that some will measure the distance differently, but it will end up the same way. So now I have the pixels. Now I can start generating array. So from now on, this is array, and your recursive ray tracing takes the I.
This array would be the pixel P
Ij.
P minus I, right? Oh, like Pij minus I, right?
Yes, and normalized, of course. Everything that I say, yes.
Yeah.
Yeah. And it's I plus this direction, that's the way.
I feel like I'm doing that, but I don't know. Maybe there's a bug, or I'm not sure how to debug.
So to start with, point to the log.
Mhm.
I can recommend again writing it in GeoGAPAs. Tells you what it is. Walk step by step with stage of path, but so far it's standard and risky. The billboard is probably harder, and you have fewer resources about it. So let's talk about the billboard.
Yeah.
But this guy, the recursive ray tracing, says where's the ray coming from, where is R, and it returns the smallest positive T that you hit. This way hits anybody. And now I forget about this UVW. There is only one way. Next, you have this equation. Squeeze from it T. Remember, R should be unit length, and of course is unit length as well.
It's the normal to the billboard, right? And
Yes, yes, and that's the direction of the ray. That's all.
wait.
But build your program properly. There is plenty of places to have bugs here.
Yeah.
One way, solve it assuming that there is only one way. And
Yeah.
to start with, assume that this way comes from 0, 0, 0, and then add the rest of it.
So for this ray, is it because the ray has like the origin in I call it origin in the direction. So like the origin would just be the I, then the direction would just be this, right?
Yes, but you're building it but you call yourself recursively once you hit a point and it's a mirror, then it will be a reflection from the mirror. If you want to do specular reflection, you want to see, or diffuse reflection, you want to ask, do I see the sun? So from the hitting point, now it's not the eye, now it's where did you hit?
It's the intersection point.
Yes.
Yeah.
So that's why I strongly suggest build it recursively and make it modular. That's
So-
all this.
Yeah, in this formula, is R just this? Is this ray R, or?
Ray has origin and direction.
Okay, so
Yes.
R is this whole thing.
Yes.
Okay.
Now, in the recursive part, you have one module that handles the spheres, one module that handles the billboards. Billboards are more complicated, let's talk about them. So from now on I have a ray, T times R times N equals this constant, squeeze T. Now, so T prime is a solution to this formula. If T is negative, you check
Then
it
you
failed.
ignore it. Yeah.
If T is infinity, which can also be the case, then it's just because the billboard is parallel to the ray. Ignore it as well, but you do have to check it when you're dividing. I don't know what will happen if you don't check and it's parallel plane. Now you have the time of the meeting.
So
Now, now you have I plus the time of the meeting times R. That's a meeting point.
yeah. To calculate T prime, could we just do lower left? Wait, it's equal to lower minus I, but then you couldn't.
You computed it. It's a constant. You have it.
Oh, it's a
stored.
constant, right?
Yeah, it doesn't care, and it doesn't have to be the lower left, upper left. It can be any point. For any point, you'll get the same constant.
Yeah.
So take this constant minus this one. That gives you T.
Oh.
Here I suggest use ChatGPT to double check yourself. So T would be, if that's C minus I dot N, what, C, whatever I have here, minus I
Yeah.
dot N
Divided by
by
R dot N.
yeah.
I think it's in the slides too. I think, yeah.
Let's continue. If you forget, then it's just standard formula of intersection of, again, ChatGPT intersection of ray and time, and how do I find your hitting point? Like easy bug to make is to say that my original direction is not a unit distance, so r is not unit length, so you'll get t, but it wouldn't be unit length, and it can, anyhow. Now you have the time. This will give you the smallest time that you hit. Sorry, I'm not correct. That's the time that I hit the plane that contains the billboard. Now comes the complicated part. So that's a part that you might lose.
Yeah, that gives you the time that you hit a point on a plane, right?
And from this time, you're getting to the point where you hit the plane.
Yeah.
Here's a billboard. Now it's a part that it starts to be critical. Lower left, lower right, upper left. Here is Q. That's a meeting point. Draw this segment. Q. F is Q minus lower left.
Is Q just this? Or
you found the intersection point. We passed this point.
what is
Q
is
I
minus
plus T prime
R?
Yes.
Yeah.
Now come the moment that you want to ask, do I hit the billboard itself? I know that I hit the, well, you checked if T is positive, and if it's negative, it just means it's beyond. Yeah. Here is F. Look at this vector U. I will use a new slide. So
Then
U,
you normalize
that's,
it, yeah.
yes, U is unit length. So U dot product F. This is.
You project U.
Yeah.
You project F onto
I
U.
compute the length.
Yeah.
I still didn't project, but at least I know what is this dx.
Oh yeah.
Now, lower left plus this number, which was U times F. Let's multiply it by U once again. This gives me this point.
U dot F. Oh, just brings Q down here, right?
It's a scalar.
Oh,
So it
yes.
tells me what's the distance. If U is unit length, how far away?
So this whole thing gives you like this length, but projected onto U.
Yes.
Yeah.
Not orthogonal projection.
Oh, orthog. Okay.
And don't forget,
Yeah, because you want
this
it
is
from.
this is dx,
Yeah.
and lower left plus dx times U is this point.
Then you
But
normalize.
let's check this dx and ask, did I pass to the right of the lower right? That's where I use this alpha and beta.
Yeah.
So take this number divided by
LR minus LL.
exactly.
And then you want it to be in between 0 and 1.
Exactly.
Yeah.
And the
you do the
same
same
goes
with
for
I.
beta.
Yeah.
Very good. And I suggest to do it in this way because now I can take alpha and beta and divide by number of rows and columns of the billboard, and it gives me the pixel identity in the billboard.
Oh, because the number of pixels is equal to the length times the width, right, of the billboard?
That's also true. No. There are two different things. So with a billboard, each billboard has its own number of rows and columns. It has n x many rows and n y many columns. If I start from, let's say that I start from the lower left, this, at which column will I be? Assume ignoring truncating order. If alpha is 0, you're in the lower left column. If alpha is 1,
Near the
that's why I said
right.
that it's, yeah.
Yeah.
That's why I said that it's important that it's not -1 to 1, but 0 to 1. So nx, now, in general, I don't, nx is part of the input thing, part of the GIF of the GIF file or read it from the file. But nx times alpha is exactly, agree?
Is it this one? Or like billboards, they only give upper left.
Yeah, but you have the reader of the PNG,
Oh,
and
yeah.
the reader tells you what is nx and y.
I think so. Yeah, I think the image data, right?
Stay with me, let's check it
Okay,
later.
yeah.
Agree, if it has nx many columns,
Mhm.
then alpha is 0, you're in the leftmost. Well, you're half a pixel off, but ignore it. Alpha equal 1, you're in the rightmost.
Yeah.
And same goes
with
for y.
y, yeah.
And now you, based on, so if the pixels are arranged from the lowest to the uppers, then nx times then bear with me, then beta, if it's 1D the way, then it means if beta equals 0, then I need to just ask about alpha. So beta nx plus, wait.
Yeah, beta nx plus alpha and
Yeah, beta
nx
yes.
plus alpha and y.
Something is.
Or is it just, yeah.
No, let's give you the ij, and now you. Let me be safe and do it in 2 steps. Ij will I equals 0, you're in the lower part, and I equals ny, you're at the uppermost. So it's I, every time that you are increasing, it's I times nx in the over, to converge from ij
Yeah.
to the 1D, that's what you did in homework 1. So it's I times nx plus j.
Yeah.
That's the index, and if every pixel is 1 volt, otherwise you multiply. So that's when it's I and j. To convert it to alpha and beta, you know how to do. I can tell you, but I'm afraid to do it online. So I is alpha times nx. I is alpha times nx. Beta is beta times and j is beta times ny.
J is beta. Yeah.
Yeah. So that's a good place to have bugs computing this alpha and beta. So start, but there is no chance to debug it if you don't have a control painting or use some debugger at a breakpoint. Like you can try, but if it doesn't work, you have no way to trace what went wrong. So that's my suggestion. Plus, I can prepare for you, or you can prepare for yourself. test scene as we said that. One billboard and the whole billboard is black, or no billboards, only spheres. See if you're getting something meaningful. It's very likely that to start with everything will be upside down, left to right. It takes time to.
So when you do the ray trace and you shoot the ray, you get the time, but then how would you know which billboard you hit?
We forgot it. Now
have to
when I have
return
this
that?
time, I need to see if this pixel is transparent. And the recursive one look at every time from every object, billboard or not billboard, ignore the times when you hit a transparent pixel that you know based on the RGB alpha. And out of all these times, which are positive, pick the smallest one. Why? Because nothing here is semi-transparent. The moment that my ray hits an obstacle, what happened at larger time, I couldn't care less. So that's in the recursive ray tracing part.
So when you calculate the minimum t, do you also return the object that it hit, or?
Why not? I mean, the JavaScript likes it. A compound, and it can. You can ask it to return the color directly as a compounding, or it will tell you at which object, or you can look at the time and then look at all the objects, depending. The slow way is just return the time, and then you need to start looking which object.
Yeah.
But this recursive call already knows what it hits, so you should
You can return
return the whole structure. Yeah, good luck.
Oh yeah, that's another. So when you do like dot product of like I or I minus, no, I think it was when you shoot the ray, you have the I, it goes to the pixel. Oh wait, no, if you multiply by t, it's just the ray is, like the t prime times the ray is just O plus t prime d. Because the origin stays the same, then it's just moving in the direction, right?
Can you repeat?
Where this is O, like the point O, and then d is the direction d. So then if you multiply scalar by ray, you only multiply d by the scalar, right?
Yes. Yeah. The term way confusing. It's the origin plus the direction. And the first time that, so I thought about this homework, and the first time that I implemented it, the I was at 0, 0, 0 because I wanted to, slowly increase the simplicity. So I prefer to do it from simplest scenario and then add the parts. But rays vectors that you multiply, and that's why it's convenient to think about everything is unit length always. So t is also it's time, but it's also the distance. It's how far away from the I you are.
How far you. And one more question. If you do a dot product, like say I dot product ray, do you just do the dot product of this entire thing, or would there ever be a?
That's to find. Then it's a constant. Like here, to find the t, it's all times. Are we
you would
finding the intersection points? Let's do it again.
Yeah.
So I plus t r
times
n is constant.
Yeah.
Okay. So k minus I dot product so items n equals k.
Yeah.
Yeah, k
Minus
minus
I
I
dot
dot n
Yeah.
equals
Divided by n dot r.
Yep. And since I don't trust myself, I don't trust myself, then let's say is a point P, here is a vector n1, n equals to n1 divided by length of n1 exactly, n1 is 5. N1 let me restart. So I got 2 points, P and Q decided n equals a unit vector of Q. So now we have a vector n. Let's look at x, y, z times n equals, I want a plane that goes through P, so equal P times n. Here is a plane that goes through P and is orthogonal to
Orthogonal to q, yeah.
Yeah. So if I take Q and this computer, something is very wrong with this computer. Do I? Was I lying to you? So maybe, yeah. So, yeah, I guess it. I'll blame the computer. It does not respond the way it should be, but yeah. And I think that it's because of that the LBS score. Very unhappy. So we can meet again, and I can double check that it all works. But